Hello everyone. In this video I'm going to be solving a couple example problems in which the differential equation that's given, it's a first order differential equation that's not exact to start with, but then through use of an integrating factor we can make it into an exact equation by multiplying both sides by some integrating factor. And then make it exact and solve it then in the way you would solve any exact equation if you've seen another video I've put up on solving exact differential equations. Alright, so in both examples that I have today, I have the same instructions. Solve the given differential equation by finding an appropriate integrating factor. Alright, so before we get into this example, let me refresh your memory here as to what an exact first order differential equation is. An exact first order differential equation is one that can take the form m of xy, right, some function of x and y times the differential of x plus n of xy, right, another function of x and y times the differential of y equals 0. So this has that form, but there's more to being an exact equation than taking that form. And on top of it, on top of being able to take this form, the left side is also the total differential of some function of two variables. And please know that the variables don't always have to be x and y. Right? You might come across other examples with variables not x and y, but I'm going to use x and y. So in order for an equation of this form to be considered exact, the partial derivative of m with respect to y must be equal to the partial derivative of n with respect to x. Okay. So we see from this example, right, so we're going to see here that this example that I have is not an exact equation. Right? So I've got this form. Right? Now the 2y squared plus 3x, that's going to be the m of xy. And then this 2xy in front of the dy there, that's the n of xy, right, from this form. But we're going to again see that it's not exact because the partial of m with respect to y is 4y. Remember, you treat x as a constant, so it's 4y. Sorry, that's a y. And the partial of n with respect to x is 2y. Right? You treat y as a constant. And these are not equal. Right? These are not the same. Meaning that the equation is not an exact equation. So if that's the case, you may still be able to do a little manipulation and make it into an exact equation through the use of an integrating factor. Now, this isn't always able to be done. Please know this. I mean, for my two examples in this video, of course it will be, but there are other examples you may come across where you're not going to be able to do this. In that case, the differential equation might have to be approached in some other fashion. Instead of analytically, maybe approached graphically with slope fields, or numerically with maybe something like Euler's method or something called a Runge-Kutta method, or Runge-Kutta. well, that's neither here nor there. We're not talking about those this time. So I'll say, if not, right, if not exact, the equation could possibly be made exact with an integrating factor. Now, here's the integrating factors. Again, now the development of where these formulas came from, I'll leave that to you to read in your text. If you're in a particular class of mine that has a text, I'm sure other textbooks besides the one my class is using also go over how to develop these integrating factors, but I'm not going to get into that. I'm just going to write out what they are. So one, if, and we'll have to check two expressions here, if m sub y, or if the partial of m with respect to y minus n sub x, partial of n with respect to x, divided by n, right, just plain old n, if this is a function of x, say capital P of x, right, just some function that's dependent solely on x and not y, then the integrating factor, I'll just call it IF, right, I dot F dot, is going to be e raised to the integral of P of x dx. Okay. Now, if this expression is not a function of just x, if it's a function of x and y or just y, then can't use it. Right? Or, just kind of changing this expression a bit, if nx minus my divided by m, if this is a function of y, say P of y, right, a function of solely y, only y, not x or not x and y, okay, not x and y together, then the integrating factor will be some function of y. Right? The integrating factor if there will be e to the integral of P of y dy. And then we'll multiply both sides of the equation by this integrating factor, and then we should have an exact equation and go from there to solve it. Right. Okay, so looking at this example, let's take a look at the first expression here in the development of an integrating factor notes that I put here. Let's take a look at the partial of m with respect to y minus the partial of n with respect to x divided by n. Well, that would be 4y minus 2y divided by 2xy. And this is 2y divided by 2xy. So this is just 1 over x. Okay. Which is a function solely of x. Right, and I'll call this P of x. And so I don't need to look at the second one. All right, what we have here is, this first expression is a function solely dependent on x. So I can find an integrating factor related to this equation. All right, so the integrating factor, I dot f, right, is e to the integral of this function P of x, 1 over x dx. This would just be x, right? I hope you see that, because it'd be e to the natural log of x, which would just be x. All right, so multiply both sides of the equation by this integrating factor, multiply both sides by x. And let's see what we get. Now it changes the equation into this. We'd have 2xy squared plus 3x squared dx plus, and then 2x squared y dy equals 0. Right. And we're going to see now that this is an exact equation. Let's see. So again, I'm treating this as my function m of xy, and this 2x squared y is my function n. It's new now, a new m and a new n. And the partial of m with respect to y is 4xy, and that's exactly the same as the partial of m with respect to x. The partial of n with respect to x would also be 4xy. And now, since these are the same, this is an exact equation. Wonderful. All right, that's the whole point of this integrating factor. All right, now that I have an exact equation, I should know how to solve it. Being an exact equation, that means that this left side here is the total differential of some function I'll call little f of xy. All right, so this first expression m would be the partial of f with respect to x. All right, because this times the dx there. So the partial of f with respect to x would be 2x y squared plus 3x squared. And the partial of this f with respect to y would be the n, the 2x squared y. And using this information, I can find what form a function f whose total differential is this side should take. So I'll start with this partial of f with respect to x. Now what I'm going to do here is integrate both sides with respect to x. Integrate WRT means with respect to x. So that'll give me this, f of xy on the left equals, and then when you integrate with respect to x, right, we're treating y as a constant. So 2y squared is a constant here, and take the integral of x, which would be half x squared, and cancel the 2. So this is just x squared y squared for the first term, plus, and then x cubed for the second term, and then plus some constant. All right, but remember the constants here are anything with y in it, because I'm integrating with respect to x. So instead of plus some c, I'm going to put plus some function of y. I'll call it g of y. And now my goal is to just figure out, well, what is this g of y? All right, so now that I know what form f will take, I'm going to now use the partial of f with respect to y, right, and to help me find this g of y and then finish the form off. All right, so the partial of f with respect to y, going through treating x as a constant, would be 2x squared y plus nothing, right, because x cubed is a constant here, plus g prime of y. And this should be the same as what I wrote out for the partial of f with respect to y earlier. This should be equal to 2x squared y, and if that's the case, then g prime of y would be 0, right, because you'd subtract the 2x squared y from both sides. And if that's the case, then if I integrate both sides with respect to y, g of y is just some constant, say c. So now we have what form the function f takes. We know what form it takes. So f of xy is of the form x squared y squared plus x cubed plus g of y, which is just some constant, so plus c. Now, just to make things a little simpler, because the left side of the equation is the total differential of any f that looks like this, I'll just simplify it and say, hey, let's let c be 0. Let's have the constant be 0. So now we go back and solve the differential equation, right? Going back to the differential equation now, back to dE, the left side is the total differential of this expression, right? Of x squared y squared plus x cubed. Again, plus some constant, but when you take the differential, it's just going to be 0 anyway, so don't need to write it. Then the right side is 0. Now 0 is the total differential of just some constant. So I'm going to use c again to represent some constant. So again, this c is not the same as that c. Maybe you'd use a different letter. It doesn't matter as long as you don't confuse them. And then integrating both sides, we get our implicit solution to this differential equation. We have x squared times y squared plus x cubed equals, some constant. And here we have an implicit solution, an implicit family of solutions to our differential equation. All right, and this should produce a solution curve, to our differential equation that we started with. Okay, for any constant. And you could solve this for y as well and get a couple explicit solutions if you want. Alright, so let me go back and let's take a look at some slope fields. You know me, if you've been watching my videos, I like to also, for a first order differential equation, I like to take a look at the slope fields and see how our solutions look, our solution curves look in those slope fields. Do they seem like they're following them pretty well? So if I'm going to enter a slope field, remember I need to solve for dy dx. So I'm going to enter here dy dx would be the opposite of the quantity 2y squared plus 3x divided by 2xy. All right, so I'll enter this into my slope field generator through Desmos. So I'll bring that up. Remember the slope, I've had this up in other videos before as well, and if you've been watching. So let's put in that expression. We have the opposite of the quantity 2y squared plus 3x divided by 2xy, and hopefully a decent slope field comes up. There we go. And then I'm going to put in one member from our family of implicit solutions. We had x squared times y squared plus x cubed equals c. All right, I'm just going to have the constant be 0 to start with and see what kind of curve comes up. There we go. And hopefully you see that this curve is kind of following along the slope field directions. If you see how these are pointing down this way, and then kind of go vertical, and then down this way, down this way. It looks like the curve is pretty reasonably following the slope fields. Right. Now I could replace the constant 0 with any constant. Let me just replace 0 here with 1, and I had to change it a little bit. Give it some time here to calculate, and look at this crazy curve, right? But you see again that I know there aren't too many lineal elements in the slope field, but the curve that comes up does seem to follow the directions of these lines pretty reasonably well. All right, you see how this little green segment's pointing this way, so is the curve. This one here, so is the curve pointing this way. And it's looking decent. And this is, again, plug in any constant on that other side. You should get a solution curve that fits into the slope field pretty well. All right. Great. So again, equations started off not exact. Then I was checking, one of these expressions, either my minus nx over n. If that's a function of x, I can find an integrating factor to help me. If that's not a function of solely x, then I'll check out nx minus my over m and see if that's a function of just y, and find the integrating factor from that. And if neither, of these work out, then you probably got to approach the differential equation in a different way, either graphically or numerically, as opposed to analytically. I mean, hey, maybe it might even be a separable equation, right? Or maybe it'll be a linear first order equation that you could solve, but couldn't do it this way. All right, now I got one other example. It's another one where it starts off in the form that I like, right? And if it doesn't start off this way, you can manipulate the equation, put it this way. So some function of x and y times dx plus some function of x and y times dy equals 0. And I'm trying to find solution curves to this that would satisfy this differential equation. And again, I'll show you that this is not exact, right? If I consider this as m of xy, this 6xy here, and consider this coefficient of the dy n of xy, you see that the partial of m with respect to y is 6x. The partial of n with respect to x is 18x. And these are not the same, right? 6x is not the same as 18x. So, yeah, the equation is in the form I like, but these partials aren't the same, so this is not an exact equation yet, right? But if it's not exact, then I'm going to check to see if there's a valid or an appropriate integrating factor. All right, so I'm going to emphasize the word try. I'll try to find an integrating factor. Not always possible, but it will be, because I picked these examples so that they would be. All right. So first, I'll check that one expression, the m sub y minus n sub x over n, and see if I get a function solely of x. Well, let's see, my minus nx, that would be 6x minus 18x divided by n is 4y plus 9x squared. So I have negative 12x over 4y plus nx squared. This is not a function of just x. It's a function of x and y. All right, so can't get an integrating factor from this. So then I gotta move to that other expression, where I just do the opposite numerator and switch the denominator n with m. All right, so nx minus my divided by m, and see if this is a function of just y. And if this is a function of only y, then I can get an integrating factor. So nx minus my would just be 12x, right? It's 18x minus 6x, divided by m is 6xy, and yes, this is 2 over y, and this is a function. Right, this is a function of only y, which is what I want. It's perfect. Right? I can now find an integrating factor, and again I'll call this p of y here. All right, so then this integrating factor is just, remember, it's just e to the integral of p of y dy. So e to the integral of 2 over y dy, which I'm hoping you can see would just be y squared, because this is 2 times the natural log of y, which would be equivalent to the natural log of y squared, and e to the natural log of y squared would be y squared. Alright, so I'm going to take this integrating factor y squared, I'm going to multiply everything, multiply both sides of the equation by y squared. Right, So let's see what that looks like when I do that. So I multiply this by y squared, that'll be 6xy cubed times dx, plus, and then this by y squared, you'd have the quantity 4y cubed plus 9x squared y squared, right? You have to distribute the y squared. Then times dy equals, and 0 times y squared would be 0 still. So now this equation, all right, the way it looks now, this should be exact if my integrating factor was correct. This should be an exact equation. Let's just double check that. This 6xy cubed, I'll call that our new m of xy. And then this 4y cubed plus 9x squared y squared, and I'll call that our new n. And you see that the partial of m with respect to y would be 18xy squared, which is the exact same thing as the partial of m with respect to x. It would be 18xy squared. So exact. This is an exact equation. Fantastic. Meaning that this left side now, again, is the total differential of some function called f. So we're trying to find this function called f. I'll call it f of xy. I'm trying to find f such that the partial of f with respect to x is this 6xy cubed, and the partial of f with respect to y is this 4y cubed plus 9x squared y squared. Right. Okay. Alright, and then just like last time, I'll start with this equation. The partial of f with respect to x is 6xy cubed. I'm going to integrate this with respect to x. Integrate with respect to x. So we have f of xy will take on this form. Now remember, when you integrate with respect to x, you're treating y as a constant. So this would be 3x squared y cubed. 3x squared y cubed. And then plus some function of y, which again I'll call g of y, like in the first example. Okay. And then I'm going to compare this to this, so take the form that f is in and take the partial with respect to y. So f sub y here should be equal to, let's see, 9x squared y squared plus g prime of y. And this should be the same as the other f sub y here, the other partial, 4y cubed plus 9x squared y squared. And you can get rid of the 9x squared y squared. Right, subtract 9x squared y squared from both sides. And that leaves me with g prime of y equals 4y cubed. And then I integrate with respect to y and get g of y must then be y to the fourth, plus some constant. But the constant this time is just some number. It's a function of only y. And then pop that back in here. So the form that f takes, right, so f of xy must be of the form 3x squared y cubed plus, and then g of y is y to the fourth, right, plus some constant. But again, I'm just to make it easy on myself, when I go back to solving the differential equation, I'm just not going to write the constant. I'm going to say let this constant be 0. Alright, so now we go back to the differential equation in question, the exact differential equation. Right, back to the differential equation. And the left side, right, this left side of the exact differential equation, the left side is the total differential of this function. And the right side, 0, is just the total differential of a constant. And then I integrate both sides and we end up with this. So 3x squared y cubed plus y to the fourth would be equal to some constant. Right? And here is and you could solve for y on this. It would be a little weird, but I'd say don't worry about it. Here's an implicit family, a family of implicit solutions to our differential equations, our differential equation. So any curve that looks like this has an equation like this. Any curve is going to, satisfy our equation. All right, and then again, just to kind of get a feel for the look of these things, let me go back to the original equation. All right, here it is. Right here. All right, so we go back to our original equation. Oops, it's off screen. Apologize. Back to our original equation, and since it's again a first order, I'm going to put it into my slope field generator. We'll take a look at a slope field. Now dy dx would be negative 6xy divided by 4y plus 9x squared. Alright, so let's enter this into my slope field generator, see what that looks like. Alright, so negative 6xy divided by 4y plus 9x squared. Alright, and hopefully some slope field comes up here. And then I'll put in one of our solutions. Right? So our solutions should look like this, where I'm just going to replace c with some constant. I'll start with 0, and you can replace it with any constant you wish, any real number. So we have 3x squared y cubed plus y to the fourth equals, and again I'll start with 0 as the constant and see what that looks like. There we go. And again, you see these slope elements are pointing up, the curve is pointing up, these slope elements are pointing down, the curve is pointing down. You have horizontal slope elements here, the curve is horizontal. So it looks like our solution curve is matching this slope field pretty well. And again, you can replace the constant c with anything. I'll replace 0 with 1. Moves the curve a bit, changes it actually quite a lot, throws this part in. And look, see these are all pointing in that direction, so is the curve, and then it gets flat here, and the little slope line is flat. These are pointing downward a little bit. This curve is going down. The curve is matching the slope field pretty well. All right, so I feel like did a good job, got good solutions to our differential equation. All right. Wonderful. All right, so hopefully, looking at these couple examples help you out when you're working on equations like this, where you can put it in the form that looks exact, but it's not exact it's not quite exact. And then you check those expressions to see, is that my minus nx over n, is that a function of x only? If so, great. If not, is nx minus my over m, is that a function of y only? If so, great. You can find these integrating factors, multiply both sides by the integrating factor, and then solve like you would any exact equation. Now, if not, right? If that my minus nx over n isn't a function of only x, and the nx minus my over m is not a function of just y, then you might have to think about some other way to approach the differential equation. Maybe it's separable, maybe it's a first order linear. Those are easier to work with. Maybe there's a substitution you could make, to turn it into a more desirable equation. Or maybe you just have to approach it graphically or numerically. Right, but hopefully in whatever sections you're looking at on exact equations, they're not trying to trip you up too much, so they'll give you examples where an integrating factor could be found. Again, so practice examples plenty until you get them down. Hopefully these videos are helping you, and thank you very much for watching.